Okay, so get up here. I'll give a word of prayer. Dearly Father, we thank you for this morning. Thank you for this class. Just ask you to just bless our work. Just help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. Let me get this pesky chair out of the way. There we go. So we're still thinking about the eigenvector technique, right? And we've started to, well, I've mentioned that there's going to be a time when eigenvectors are not enough, right? And as I mentioned, two obvious, like sort of, well, one very obvious problem is going to be that the characteristic equation has a complex solution. Something else, something funny has to go on there. But before we even get to that, something else can happen. We might not have enough eigenvectors to form our solution. So I want to try to get to that today. And I'm going to start with an example that shows you the problem, perhaps. So here's example one. We could be up against something like x, y, z prime equal to, let us say 3, 2, 0, 0, 3, 0, 0, 0, 7 times x, y, z. All right, so I'll take it easy on us. This example is not too hard. And this serves to illustrate one of the things I said last class, which is, if you've got a triangular matrix, finding the eigenvalues is super easy. Like, without further calculation, I can tell you the eigenvalues of this matrix, right, are what? I mean, I'll do the calculation, but a minus lambda I. You got 3 minus lambda 2, 0, 0, 3 minus lambda 0, 0, 0, 7. Oops, minus lambda. Don't forget my minus lambda. And so properties of the determinant, you just multiply the diagonals, and we've got, 3 minus lambda squared times 7 minus lambda. So therefore, lambda 1 equals to 3, and lambda 2, let's say, is equal to 7. And let me introduce a concept here, which is the algebraic multiplicity. So here, this right here has algebraic multiplicity 2. So the algebraic multiplicity refers to how many times the root is repeated in the characteristic polynomial, if it is at all. All right? Okay, so let's do the easy part. Let's find the eigenvector with eigenvalue 7. What are we up against here? Let's say lambda 2 equal to 7. I'm looking at a minus 7i times, let's say, I'll call it u1 equal to 0. This gives me the matrix minus 4, 2, 0, 0, minus 4, 0, 0, 0, 0. And I'm going to put u, v, w as the components of that vector I'm trying to find. All right? So how should we solve this system? Like, let me just tell you, the easiest way to solve this is bottom up, right? So notice that the last row forces that w is equal to 0. That's forced upon me, isn't it? Oh, wait a minute. Is that true? I mean, yeah, the last row doesn't tell me anything, right? The last row is a 0 equation. It puts no restrictions whatsoever. Actually, there's no condition on w from that. how about the second row? Let's start there. That tells me minus 4v equal to 0. So therefore, v is equal to 0. We're stuck with that, right? And then if I work my way up to here, I get minus 4u plus 2v equals to 0, which tells me that u is equal to 0. All right? So we've got u equal to 0, we got v equals to 0. Why would it be wrong to put w equal to 0? Can you guys tell me? If I put w equal to 0, what would I have just done? Well, that would be the trivial solution, right? So, and that would not be an eigenvector. So we need u1, which is, by the way, uvw, not equal to 0, right? That's what we're after. Is there a trash can back there? I haven't hit anybody yet this semester. So, or ever? No one knows, really. Seems like it must have happened at some point, at least off the ricochet, you know? So, W is free, right? So, imagine Trump gets elected. W's free. So, sorry, too soon? I made the mistake of watching.
I think you just got canceled.
I think I just got canceled. It's a good thing this isn't a live stream.
All those on the way here right now.
But like her way of speaking, it's just, I just want her to stop. Just stop talking. Just don't talk. Anyway, so W is free. So we might as well put W equal to 1. That's a choice, right? And so we'll have U1 equal to 0, 0, 1. There was once upon a time that I accidentally spelled that in a math class by accident in a calculation. They were laughing all of a sudden. The whole class is laughing. I'm like, what? And I turned around and I looked at the board and I was like, oh, children. Of course, by then they had already had their phones out and taken pictures. So, anyway. If you come to office hours, I'll tell you how that happened. Okay, so this will not help anyone. So that's eigenvalue 7, eigenvector. All right, great. And from this we can create like a first solution. Let's say x1 of t equals to e to the what? E to the 7t times 0, 0, 1. Like that's the solution that gets us, right? Now it's not the general solution because there should be 3 independent solutions here, right? That's just one of them. So what's up next? What's up next is eigenvalue 3. Next we'll try lambda. Maybe I shouldn't try speaking today. Lambda 1 equals to 3. And so there we're going to look at a minus 3i times, let's say, u2 equal to 0. Now what's that look like? A minus 3i, you subtract 3 from the diagonal. So you can, if you did the characteristic equation right, you can always go back to there and just plug in lambda equals to 3 to see what happens. So you get like 0, 0, 0, 2, 0, 0, 0, 0, and 0, 0, 4. Wow, these are even easier to solve, right? Check this out, yeah? All right, so the middle equation this time, totally trivial, right? And the top and the bottom equations, they're just kind of like, well, 2v is equal to 0, and apparently 4w is equal to 0. So therefore v is equal to 0. and therefore W. Uh-oh. It's the middle one. So like when we multiply this by that, we hit the V. In fact, U is free here, I think. Is that right? Huh. Oh, I guess that's good. So U is free, which means that our general form for U2 has the what form? It's just what? It's like U 0, 0, right? So we can get 1, 0, 0 if we set U equals to 1, right? So therefore, my U2 is 1, 0, 0, right? And so that tells me that I get a second solution. My second eigensolution, e to the 3t 1, 0, 0. So there you go. I've got one solution. I got two solutions. Where's my third? Where's my third solution? But we need linearly independent solutions. I can't just use another one of these. Yeah. So this matrix is an example of like this matrix. So here, let me tell you what's going on here in terms of like the linear algebra. A is not diagonalizable. What happened? Oh, okay. So A is not diagonalizable. A matrix is said to be diagonalizable if you can find P such that P inverse AP is equal to a diagonal matrix. If it's possible to find P like that, then that matrix is said to be diagonalizable. From the calculations we've done and the theory that you'll hopefully study in Math 221, this matrix is not diagonalizable, right? And what that means is that there's not enough eigenvectors, right? The way you diagonalize the matrix actually is you just make P a matrix of eigenvectors if you have them, right? So if you have enough eigenvectors, you can diagonalize the matrix. We can't do that here. So what do we do? What do we do? All right, so I'm going to have to take a brief theoretical tour here for a bit, and I need to introduce some theory that we haven't done yet, and so let's get into it. So definition. Given, dr dt equals to AR, we define a solution matrix to be a matrix of functions let's say big X such that each column is a solution to star. Let me give this a name here. We'll call our differential equation star, so I don't have to keep writing it. All right. Each column is a solution to star. And I should be clear. It's not just any old matrix. It's a special kind of matrix. It's a square matrix. So let me weasel a word right in there. Square. All right. So, for example, I could make a solution matrix here. Here would be a silly one. I could do like x1, and then I can put x2 next, and then I could put like 2x2 there, right? So like for my current problem, my current example 1, I'd have a solution matrix of like 0, 0, e to the 7t, e to the 3t 0, 0, 2 e to the 3t. All right. Now this kind of solution matrix we wouldn't actually be very interested in. We're mostly interested in a solution matrix if it is what's called a fundamental solution matrix. If the determinant of x is not equal to 0, then x is a fundamental solution matrix. So like that condition, the determinant of x not equal to 0, what that means is that the columns of x are linearly independent. And in fact, this determinant is nothing more than the Wronskian of those n columns. Going back to the Wronskian I introduced like a couple classes ago. So this would be a fundamental solution matrix if the determinant is 0, which is another way of saying if the matrix is invertible, it's a fundamental solution matrix. Now the one I just wrote, right, my example 2, I guess, although maybe this is example 1.3. I don't know. It's still part of example 1. That is not a fundamental solution matrix. Why? Fun fact for you guys, if you have one column as a multiple of another, the determinant's 0. Anytime we have one column is simply a multiple of another, that makes the determinant be 0. So you can check the determinant of this guy is 0. So not a fundamental solution matrix. Now, I need to also share with you a little bit of linear algebra here. If we have A, let me put it up here. So if I have A, matrix A, times x, right? And so I've got A times, we're going to say x1 is the first column, x2 is the second column, and so forth and so on. Xn is the nth column. The way matrix multiplication works is there's a column by column multiplication rule. So when you sort it out, this actually is equal to ax1, ax2, axn. This is actually how matrix multiplication works. All right? How should we define the derivative of a matrix? What do you guys think? What should the derivative of a matrix mean? So here I'm thinking of x1 through xn as being themselves vectors of functions, right? Solutions, in fact, to the differential equation in question. So the derivative of a matrix should be simply the derivative of each component in the matrix, right? Like that's how we differentiate a matrix. And so one application of that is that if we differentiate, a matrix that's formed by these n columns, then we have the derivative of the first column, the derivative of the second column, the derivative of the nth column. Now, lest you think I'm just telling you fun linear algebra for no particular reason, there is actually a reason here. Check this out. If I write dx dt equals to ax, right? This is equivalent to the matrix dx1 dt, dx2 dt, until dxn dt equals to, what was ax? Well, we got it right there, right? So ax1, ax2, axn. But if two matrices are equal, right, that means that they have to be equal column by column by column by column. Every column of the left and the right has to match up. So I can trade this one matrix equation for, in fact, n vector equations. See, it's the same as if dxj dt is equal to a x sub j for all j ranging from 1 to all the way out to n. That's for all. I'm sure some math professor did it to you somewhere. Sorry if that is the first time you're seeing for all, but I don't think that's probably the case. Well, well, well. My apologies. Come on, shush. Well, it's my mom. I can allow it. There's probably going to be another text. I probably should have muted it. Okay, we're good. So my point to you is if we can find a solution matrix, right? If we can find a matrix that differentiates to the same pattern as the differential equation, we've found not just one solution, but n of them. Right? So that begs the question, what is the solution matrix to the problem that we're facing? Like, is there some general overarching, this is the solution to every one of these problems, matrices? Could it be that simple? Right? Could it be that simple? So that's the question. Can we find a solution matrix to dr dt equals to AR? I mean, there's one way we could do it, right? We could just take the solutions we've already found and paste them together. That's kind of boring. That's not really what I'm after. What I want is I want to find a solution matrix which fills the gap in example 1. All right? So I'll show you how I show you what we do. So here's a little motivating comment. So here's some motivation, perhaps. What if you guys were asked to solve, I don't know, dy dx equals to, let's say, maybe dy dt rather, is equal to, let's say, a times y. Could you solve that? So this is the n-dimensional version. This is the one-dimensional version. Can you solve the one-dimensional version? What's the solution? I think we've done it in here already, right? Like we go dy over y is equal to a dt, right? And then you do what? Integrate that thing. That gives us natural log the absolute value of y is equal to at plus a constant, which then tells me that y is equal to like some constant times e to the at, right? So basically, like, my takeaway from this little calculation is that e to the at is like a fundamental solution here, right? So y1 equals e to the at is solution to, one-dimensional case, right? So if this works, what would we guess? How about this? X equals to e to the t times the matrix A should be a solution to the differential equation. But this begs a question. What on earth do we mean by e to the ta, right? How do you take the exponential of a matrix? Care to guess? So the answer is this. One of your favorite things from Calculus 2. We do n equals 0 to infinity of ta to the power n over n factorial. In other words, we're going to define the matrix exponential by its power series. So I'll write it out. So lowest order, we get the identity, then we get t times a, then we get 1/2 t squared a squared, and then you got 1 over 3 factorial t cubed a cubed, and we could go on here, right? And so forth and so on. All right. You can prove that this series of matrices converges for any matrix. This can be proved. The proof of it rests on the fact that the exponential series of an ordinary exponential function also converges. And of course, you got to come up with like what's the length of a matrix in order to make sense of that word I use, convergence. But the length of a matrix can just be thought of as like the square root of the sums of the squares of the components, as if the matrix is just an n squared dimensional vector. Like that's a way you can give concept make rigorous that concept. But that is for another course. So, for example, that's the kind of thing I would probably delve into in advanced calculus. I'm not helping sell that course right now. No, everything in advanced calculus is super easy. You should come take that course. It's hardly a proof to be seen in there. It's just fun new calculus. I'm not sure I even give tests in there. I think everyone just gets an A. You know, it's just like, no, sorry, I'll stop. Okay, so what do you think dx dt is? It's really like it's a horrible name for a course though, by the way, guys, like advanced calculus. Like it's like that name kills the course. I should come up with a different name. It's really no more advanced than most of the other courses you take at the junior or senior level. But anyway, dx dt, what you can do is you differentiate term by term. So what's the derivative of the identity matrix? 0. What is the derivative of t times a? So dt is 1, and you just get a. And then we get 1/2 of 2t, and there's an a squared. So the a is constant. It just rides along, okay? And then you get 1 over 3 factorial times 3t squared a cubed, all right? All right, so let's factor an a out, right? Factor that a out. What do we got? We've got the identity matrix. So a times the identity matrix is equal to the identity matrix, guys. Like it's like the number 1, the way it works. So I factored an identity matrix out of the first a. I've got 2 a's in the second one. So that gives me plus ta. And what's 3 factorial multiplied by 3? Well, it's 1 over 2 factorial, right? So plus 1 over 2 t squared a squared. And if I had written the next one down, we'd have 1 over 3 factorial t cubed a cubed. And this goes on. What is this? What are we looking at? It's just the what? It's the thing we started with. This has a name. This is the matrix exponential. It is e to the ta. What does this calculation mean? This means that the matrix exponential is a solution matrix to star. Every column in the matrix exponential is a solution to our system of differential equations. Which matrix does this work for? All of them. This is a universal solution to the problem dr dt equals to ar. So then, why don't I just start by teaching you that? What's the rub? Well, the rub is how do you actually calculate an infinite series of matrices, right? How do you actually compute this infinite series? Yeah? All right, so I'll show you. I ought to be careful not to erase my, I should probably keep that. Let's see here. All right, so here's the thing that makes it, I mean, we could do an example where we just straight calculate it, all right? And we'll do that, but I don't want to do that right now because I do want to circle back to example 1 before we get out of here today. I want to show you how it finishes example 1. So, but I do have some more theoretical development that I have to do before we get there, all right? So stick with me here. So here's an identity we can write down for the matrix exponential. We can write down e to the ta is equal to e to the t times a minus lambda I plus lambda I times t. Now, the situation, guys, is this. If we do e to the a times e to the b, it turns out that that's equal to e to the a plus b plus 1/2 the commutator of a and b plus 1/12 the commutator of a with the commutator of a and b. Oh, fine. Plus 1/12 b commutated with b commutated with a plus dot 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 dot. So like this thing I just wrote down for you, first of all, it's probably not true in some sense. Like, I really got to put a plus or minus here. I'm not sure whether it's a plus or a minus. I don't remember the formula that well. This is the so-called Baker-Campbell-Hausdorff relation, BCH formula. If you're wondering, this is the commutator of A and B. By definition is AB minus BA, right? So basically what the commutator does is if two matrices, when you multiply them, it doesn't matter which order you multiply them in, they're said to commute, right? So the commutator of two matrices is 0 only if and only if they're commuting matrices. So notice what this formula does. This formula truncates. It's just e to the a times e to the b is e to the a plus b in the special case that the commutator of a and b is 0. Otherwise, there's this actually unending series of correction terms from the fact that a and b don't commute. All right? Fortunately for us, we are in the commuting case, you see, because if you think of like all of this right here, I should have used something other than a and b. Let me put a bar here. A bar, b bar, 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 bar. Okay, there we go. Bar, 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 bar. So if you think of this as a bar, and you think of this as b bar, well, these commute, you see, because this is a number times the identity matrix. And a number times the identity matrix will commute with anything else. All right? So like it is true that a bar b bar is equal to b bar a bar. And in that case, I'd have the plain old law of exponents. So I'll do that. So don't worry, like at no point in this course are you going to need to know this formula. I'm just sharing with you. I think it's interesting. It lies at the heart of like quantum mechanics. In quantum mechanics, you have physical observables that act on state vectors. Those things are operators. You can represent them by matrices in the Heisenberg formulation. And the this formula here relates how those representations of the Lie algebra act on the group of symmetries and so forth. So there's like deep physical meaning to this formula, right? But we just need the commuting case. And so here I have e to the lambda it. I could have just added the lambda. See, guys, I'm sorry, I messed this up. I should have added the lambda it before that rather than after it. You see, I could do that up here, right? So if you can imagine, just let me put that over here if you don't mind, because I want to put this first. And then I have e to the t times a minus lambda I. All right. Now, if you work this out, and I'll try to do one of these another day, this is actually going to just be e to the ordinary exponential, like e to the lambda t, times the identity matrix. That's actually how that works out. And this here, and when I have the ordinary identity matrix, I can just not even write it. All right, like I don't even need that there. I can just write it like this. Just getting straight to the point here. This is again a matrix exponential, so I can write it as a series of matrices. So you start out with the identity matrix, and then you've got t times a minus lambda I plus t squared over 2, a minus lambda I squared, plus 1 over 3 factorial, there's a t cubed here, a minus lambda I cubed, and so the story goes. Right? So this, my friends, this formula right here, this formula, to use a vernacular, your vernacular from your generation, this formula here, it's fire. It's fire. I usually call it the magic formula because it's also magic. It's magical what it does. All right? So if you ever hear me talking about the magic formula, I'm talking about this. All right? How can we use the magic formula? Let's see what happens to the magic formula when we do something like, I don't know, feed it an eigenvector. Let's feed it u1. What happens? What happens when I look at e to the ta times u1? And I'm going to look at the magic formula with lambda equal to, well, 7, to make use of u1. So suppose I have e to the ta times u1. So that would be e to the 7t times I plus t times a minus 7i. And if you don't mind, I'm going to multiply u1 through the series. So I have like I times u1, and then plus this times u1, and then plus like t squared over 2, a minus 7i squared times u1 plus da 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 da. What's happened over there? What's happening over there in math major land? Something.
We're trying to decipher.
Trying to decipher it.
Yeah.
It's fire. I told you already. You think it's strange fire?
A little bit.
It is a gift. That is true. So a little cessationist humor there for you. I'm not really a cessationist, though. Anyway, don't worry, I'm not going to start talking in tongues today. Just English, maybe some math. So what is a minus 7i times u1 equal to? I've erased it, but we worked it out, right? A minus 7i times u1 by construction was 0, folks. That was how we constructed u1. We solved that equation, right? So, and what does that say then? If the first one's 0, how about the second one? Multiply it by the matrix again. That's also 0. And the cube, and the 4th power, and the 5th power, and so forth. And so, in other words, all of this, big fat 0. And what are we left with? What are we left with? We just get that. Almost like I planned it. So if you take the matrix exponential times an eigenvector and look at it from the guiding light of the magic equation, you get back the eigensolution. All right? Okay, so how does that help us solve this problem? Well, not done yet. So that brings us to our next item for today in terms of theory, which is I think I can get rid of this at this point. I'm probably going to regret that. We don't need this. All right. So definition. A set of non-zero vectors, let us call them v1, v2, vk, is a k-chain with eigenvalue lambda for A if, let's say, A minus lambda I times v1 is equal to 0, and A minus lambda I times, let's say, vj is equal to vj minus 1 for j equals to 2, 3, all the way out to k. Okay. So in this context, what this is going to make, it's going to make each one of these vectors, v1 through vk, what's called a generalized eigenvector. So a generalized eigenvector, v is a generalized eigenvector of order p if, with eigenvalue lambda, if A minus lambda I to the p minus 1 acting on V is not equal to 0, yet when we take the pth power acting on V, we get 0. So for example, eigenvectors are generalized eigenvectors of order 1. Kind of boring, right? But this chain condition that I've put right above will actually make each one of these things in the chain, in my current notation, like Vj will be a generalized eigenvector of order j as I've set it up. Let me show you why that's true. So like, so let's look at the, so first of all, by definition, the first one's an eigenvector, right? How about the second one? A minus lambda I times v2 is equal to v1, right? By assumption, that's non-zero, right? That was, we assumed, non-zero vectors. What happens when I multiply this by a minus lambda I a second time? So I'm just multiplying the equation above by a minus lambda I on both sides. What do I get? Remember, a minus lambda I times the eigenvector is, by assumption, 0, right? That's 0 on the right-hand side. So what do I have? I have a minus lambda I squared on v2 is equal to 0. So what's this all mean? Thus, v2 is generalized eigenvector order 2. Because the square matrix a minus lambda I acting on it gives me 0, but the first power does not. We could go on. We could show, likewise, if you calculate a minus lambda I, like, say if a minus lambda I v3 is equal to V2. That implies that A minus lambda I squared on V3 is equal to what? If I multiply by A minus lambda I, it takes the V2 and it knocks it down to V1, which then implies that A minus lambda I cubed on V3 is equal to 0. So V3 is a generalized eigenvector of order 3. And so the story goes all the way up to k. K is a generalized eigenvector of order k. Right? All right. The reason this is interesting, guys, is if you look at the magic formula, what do these chain conditions do? See, if you look back here at the magic formula, notice what happens, like, what would happen if we had a, for the sake of discussion here, suppose we had, I'm going to put it up here, because everybody can see it if I put it up here, right? And we don't need this anymore. Ugh. What if I had A minus, let's say, 3i times u3 equals to u2? Remember, u2 was a generalized, u2 was an eigenvector with eigenvalue 3, right? We worked that out earlier today. If I could find a vector like u3, what would the magic formula do? Check it out. So like then I'd have e to the ta times u3, right? And I put the magic formula with lambda equals to 3 because I'm after the eigenvalue 3 solution. So e to the 3t. So I'd have I times u3, which is just u3. And then I'd have plus t times a minus 3i u3 plus t squared over 2 a minus 3i squared on u3, and then plus stuff. But just going through just what I went through in general, what is this? This tells me what? A minus 3i squared on u3 is what? It's 0, right? That's 0. And that means that the cube acting on it is also 0. And the fourth power of that matrix is also 0. In other words, all of this stuff, big fat 0. How about this right here, though? Not 0, but what? u2. So this would be e to the 3t times u3 plus t times u2. And you see that right there is the third missing solution that we haven't found yet today. That is the missing link. That's all that we're missing from our general solution to example 1. So, sadly I'm out of time, but all we need to do to finish the solution to example 1 is do what? We just need to solve this equation, which we can easily do. Because this is just a matrix times a vector we don't know equals to a vector we already know. We can solve that system of equations, and we'll start next class by doing that. Okay, guys? So I'll stop here. But we probably will have a quiz next class. Probably not. Quiz would not be on the magic formula. Like the quiz would just be on like eigenvectors. All right. So more like the 2x2 example we did probably.